In chapter 1, we saw that quantum objects can be described by waves. According to the de Broglie postulate, electrons, even things as large as C60, can be described by a wave representation, and things that can diffract and interfere with each other. And so before we start talking about the wave functions that are part of quantum objects in the next rest of the class, in chapter 3 and beyond, we're going to take a step back and look at solving wave equations in the classical sense. So there are things that we describe classically as waves, and we can look into some of the tools mathematically that we use to understand these classical waves. Things like a vibrating string is the main model we're going to look at. Many of these tools are going to be useful as well when we're thinking about quantum mechanical objects. And so working with something we can actually visualize and understand will help us to get a better sense of what's going on when we get to things that are less in our experience, like electrons acting as waves. And so this is this chapter serves as a background there. And so the model we're going to look at for most of this chapter is a vibrating string. So we're going to imagine a problem where we have a string. So we have two walls, and we have a string that's stretched between these two walls, and it's fixed on either end. And so we're going to describe the distance from one wall to the other as x, starting at 0, going up to a length of L. And we're going to consider how far is the string displaced from resting as a function of x and t. So we're going to call this u. U is how far the string stretches up or down along the length of the string. And u will depend on how far we are along the string. Obviously, at the walls, it's going to be fixed. That's the definition of the problem. And it's also going to depend on time, right? So this string will vibrate as a function of time. And we'll see there are many different ways it can vibrate that works. So the string is fixed. And it will vibrate from its resting position, can be displaced. And this function u is a function of x and t is our function that we would like to solve for. We'd like to understand how does displacement change as a function of x and time. And so there are many possible solutions. So for example, one possible solution that we'll see is that the string can start vibrating upward, and then over time move downward until it's even and starts going downward, right? And so this is one possible solution, is that the string will be going sort of back and forth, vibrating sort of like half of a sine wave, moving up and down. And this is, if we take time and keep moving this way, we'll see the string will go up and down, and we assume that there's nothing causing the string to stop vibrating. In reality, the air will get in the way, and eventually strings stop vibrating. But we're taking the simple case where we're not worrying about that. So classically speaking, we can show, we won't derive where this part of the equation comes from, but to describe this, the string has to satisfy a partial differential equation. And so the equation is that the second derivative of this function of x and t with respect to x is equal to 1 over some constant here, 1 over v squared. We're going to solve for this constant, times the second derivative of this function of the displacement with respect to time. So this is what's known as, this is the classical wave equation. Okay, and so generally when we have differential equations like this, and this will show up when we're looking at quantum objects as well, quantum systems, there are generally some sort of physical constraints on this system that we call boundary conditions that will limit which possible solutions of this equation actually satisfy our specific system that we're looking at. And so in this case, for this setup that we have, the boundary conditions are that the string is fixed on either side. And so that puts some constraints on the possible solutions that we have. And so the way we write this is we want to think of, okay, how do we say mathematically that the string can't move? And so what we can say is that u, when x equals 0, on the left-hand side of the string, u, when x is equal to 0, and at any time t, so at any possible time we have, has to not be displaced. That's what the string being fixed means. And we can say the same thing when x is equal to L, right? At the far right side, where the string is attached to the wall, u at length L, at distance L, at any time is equal to 0. And so this is for all values of t. All right, and so this is sort of our setup that we have for the rest of this chapter, thinking about this string under these boundary conditions.